Right, so chapter 6 deals with the concept of an inner product space. We have actually already dealt with a type of inner product space, but we're going to formalize the definition of an inner product space. Remember, we took a vector space and we took the dot product on a vector space. And that in itself is, in fact, a type of inner product space. And so we're going to formalize the definition of an inner product space in chapter 6 and section 6.1. So let's just quickly recall some definitions. So just recall that the dot product was defined as follows. So we had the vector in U and Rn, two vectors u and v, and then when we take the dot product, we simply took the product of component-wise of each of the two vectors, and then we all added it together, and that is the dot product. And we had some applications for the dot product as well. It's a useful way of finding the angle between two given vectors. So that was the dot product. Now, recall that the dot product had the following properties. Taking the dot product of u with v is the same as taking it with v with u. Also, if you have three vectors, the dot product distributes over the sum. So in other words, if you take a dot product with a sum between two vectors, it's the sum between the respective dot products. Then we also had the scalar multiple property, where if you take a scalar multiple of a dot product between two vectors, it is the same as taking the scalar, you take the scalar multiple of the one vector and you take the dot product with the other vector. And then we also had that always dot product between a vector with itself is always bigger than or equal to 0. And the only way that the dot product of a vector with itself is 0 is if the vector itself is the 0 vector. Right. Okay, so those were four properties that related to the dot product. Okay, so now we're ready to formalize the definition of an inner product. So keep the dot product in mind while we are going through this. So general inner products are defined as follows. So what is an inner product? An inner product on a real vector space V is simply a function that associates a real number, let's call the real number that number, with each pair of vectors in V, in such a way that the following axioms are satisfied for all vectors u, v, and w in V, and also all scalars in K. Now remember, when we looked at vector spaces, there were those axioms that we talked about, all the axioms that needed to be satisfied for a set of vectors to be called a vector space. Now these, the four listed axioms, are the axioms for inner product, for an inner product. So 1, 2, 3, and 4 needs to be satisfied for a given operation to be called an inner product. So just like the dot product, you need an inner product between two vectors u and v to be the same as the inner product between the vector v and u, right? Just like the dot product. Right, so and then this, if you take the inner product of a sum between two vectors with a third vector, then the sum that particular inner product needs to distribute in this way. So basically, it essentially boils down to the sum of the two vectors u and v. If you take the inner product of that with the vector w, then it's pretty much taking the inner product of each term in the sum with the vector w, and then summing the two inner products together. So that is how the sum needs to distribute. And also, if you take a scalar multiple of a vector and you take the inner product with another vector v, then that's just the same as taking the inner product of the two vectors u and v separately and multiplying that with a scalar k. And then also the inner product of a vector with itself is always bigger than or equal to 0. And you have that the inner product of a vector with itself is exactly equal to 0 only if the vector v is the 0 vector. Okay, so if v is the 0 vector, then the inner product of v with itself will be 0, and vice versa. If the inner product of v with itself is 0, it's going to immediately imply that the vector v needs to be 0. So that is what a inner product. That's what an inner product is defined as. So the dot product is a special type of inner product, and it's one specific inner product that we've dealt with primarily so far. Now, a real vector space with an inner product is called a real inner product space. Right, so remember, with a vector space you had two operations. You had the addition operation and the scalar multiplication operation. So now if you take a vector space and you add an additional operation, and this operation you make it an inner product, then you call the resulting space a real inner product space. And that is if it's a real vector space. Okay, that brings us to theorem 1, which gives us some additional properties of an inner product. So given three vectors u, v, and w in a real inner product space v, and given that k is a scalar, then number 1, we've got that the 0 vectors, if you take the inner product of the 0 vector with any vector v, that's the same as taking the inner product of v with the 0 vector, and that is always going to be 0. Then if you take an inner product of a vector u with a sum between two other vectors v and w, then it is the same as taking each term in the sum and taking separately the inner product with a vector u and then adding the two together. So note the similarity between this property and the other property we talked about, which said that if you have a sum between two vectors u and v, and you take the inner product with a vector w, then the sum distributes in that way. Okay, but you can actually, if this term here is a sum, then it also works in. It also works the other way around. So that is going to be v inner product with w. Okay, so remember this was one of the that was one of the axioms we talked about, and this axiom is very much very much related to this property here. Then the next property, if you take the inner product of a vector u with the difference between the vector v and w, then again that is the same as taking each term in basically in the sum between v and minus w, and taking each term there and taking the inner product separately with u and then adding the two together, and then this negative sign comes into play as well, and primarily the negative sign, if you go back to this property here, that comes from the third axiom. Then also we've got, if you take the difference between two vectors and you take that inner product with a vector w, then again the difference there distributes in that way there. And then lastly, if you take the scalar multiple, or if you take a scalar and you multiply it with an inner product between vectors u and v, that's the same as taking the vector u and taking the inner product, the u's inner product with the scalar multiple of v, where the scalar is k. All right, again, and note that previously the axiom we looked at, the previous axiom, it's very similar to this result here, and we only looked at that with respect to the vector u. But the scalar, I mean, that is also, according to this theorem, that's also the same as doing that, taking the scalar multiple of the vector v. Okay, so what I'm going to do is I'm just going to look at the proof of, I'll look at the proof of 1, let's look at the proof of proofs of 1, 2, and 4 and 5. So let's take, I'm going to leave the bars out. You guys, I mean, we assume that these things are all vectors. And what we're going to do here is prove the first property. So note that we can write this as the 0 vector plus the 0 vector in a product with v. Okay. Now, according to one of my axioms, the sum distributes in the following way. It becomes that, and we will just list the axiom that we're using here. Okay, so that becomes inner product 0 with v plus inner product 0 with v. Now, from where does that come? Right, that comes from axiom 2. That comes from axiom 2. So let's just keep track here. So that comes from axiom 2, right? Okay, that is from axiom 2. Now, what can we say from here? So this implies that we can take this. This is a real number, okay? We can take this number here, and we can subtract this real number from there. Okay, and this is also a real number. This is also a real number, right? So that's also a real number. Okay, I've not changed. What I've done on the left, I must do on the right. So I subtracted on the left inner product of 0 with v. So what I need to do is I also need to do that on the right hand side. Okay, so that's going to imply that this part here is going to become 0. Okay, and this part here is going to become 0. So essentially what we have is we've got that becomes that, and that term falls away there. So therefore we've got our first result of our theorem. Okay, so there we go. So a 0 inner product of 0 with v is always 0. Right, so the second property, let's look at the inner product of u with v plus w. Now we know from axiom 1 that the following holds. So you can switch the two around, and the inner product is still going to be the same. Right, so we have that, and that comes from axiom 1. So uv is the same as vu. Okay, and therefore again this just distributes in according to the way that the sum distributes, and again that comes from axiom 2. the fact that the sum distributes in that way. Okay, so that comes from axiom 2. And that is going to be, okay. Apply axiom 1 again to both the inner products I have in my sum. So I can go and switch those two terms around. And basically we've got this here. And again, we switch the terms around again, U and W. Okay, and from there, right, so therefore that comes from axiom 1, and so we have proved the second part of our theorem. Okay, so the third part, again, you apply the second part that you've already proved. So we have that you can express that inner product as just basically the inner product of U with V plus the vector minus W. Okay, and again, remember we said that according to our previous result, that is just the inner product of U with V plus the inner product of U with negative W. Okay, and that you can write as the inner product of U with V plus the inner product of minus W with U. And again, what is that? That's axiom 1 that we applied. Okay, and from there we can then say that U, inner product of U with V plus the inner product of minus 1 W U, and again, what can we write that as? You can write that as that, and what you can do now is you can apply the third axiom. You can take that out there, and you can basically take that scalar multiple and you can apply it on the outside, and we have that situation there. And then again, that you can write as UV plus, or rather minus UW. And again, what we've used now is we've basically used axiom 1 there, and if you look at this axiom here, that's a scalar multiple axiom, and that's axiom 3. Then last property is property 5, and that's the scalar multiple property. Right, so if you take the scalar multiple of the inner product U with V, alright, so if we take a scalar multiple of the inner product of U with V, that's the same as taking a scalar multiple of the inner product of V with U, and this comes from axiom 1. Okay, that comes from applying axiom 1. So we're replacing the inner product of U with V with the inner product of V with U. And this then applying the third axiom, we get then that we can replace that with the scalar multiple of K with V with U. Okay, and then applying axiom 1 again, we can go and basically switch the two around. So we can switch the two around there. And then prove my result. Right, so again, as we said previously, the dot product in Rn is also commonly called, it's called the Euclidean inner product, because the dot product is by definition, the dot product satisfies the axioms of an inner product. And so therefore it is called an inner product, or it's also called the standard inner product. Now we call Rn with an Euclidean inner product, we call that Euclidean n space, just so that you know. This brings us to just the concept of a weighted Euclidean inner product. This is a special type of inner product, and it's called the weighted Euclidean inner product. So it uses the dot product, but it adds weights to it. So if you're given a sequence of real numbers w1 up until wn, they're all positive real numbers, and those we will call the weights, and you're given two vectors u and v in Rn, then we can define a special type of Euclidean inner product. And how this inner product works is essentially it takes the dot product of u with v, right, and then each term in the dot product sum, we multiply it with this each term, respective term, with the weight. So it works very similar to the dot product, but it just adds the weights. And that in fact satisfies all the definitions, all the axioms of a inner product, and therefore it's called it is an inner product, and it's called the weighted Euclidean inner product with weights w1, w2 up until wn. Okay, so let's just prove in this first example here. Consider the right. So consider this example here. If we look at the weighted Euclidean inner product on R3 with weights 2, 1, 3, they ask us to show that this function satisfies the axiom of an inner product. Now, what I'm going to do as an example is I'm just going to show that in general this operation is in fact an inner product. Here's my weighted product, and we're going to show that this is an inner product. Okay, so again, what do we do? Essentially, what we do is we take the the dot product of u and v essentially, but we modify this by introducing these weights by multiplying each term with w1, w2 up until wn respectively. So let's just quickly make sure it satisfies all my axioms. So to check the first axiom, we take this term here and we just observe that we can basically write that as we switch the two around there, u1 and v1. Surely we can do that. Then we've got w2, which again we switch those terms around, and we can do that in general. Okay, so there's my v2, and there's u2. Okay, and we do that up until the last term, where we've got wn, and we okay, and that is pretty much just the inner this product that we take of V with U. Okay, so the first axiom holds. The second axiom, we introduce an extra vector R, and we look at the product of U plus R with V. Now, if we go by definition, right, so we have that product is in fact it's U plus R, so it's the first component of U plus the first component of R, second component of U plus the second component of R, and we go up until there, and we take the dot product with V, okay, and then we introduce each one of the weights. Okay, now we can just go and simplify this term, and that becomes we first gather the U terms, okay, and then we gather the R terms. Gathering the R terms leads to these two sums, okay, and these two sums can be replaced with the following. That term there, we can replace with the product of U with V. Second term we can replace with the product of R with V, and we're adding it together. So the second axiom holds. The third axiom, take a scalar multiple of the product of U with V. That is straightforward. That is going to be that's going to be K multiplied by this whole term here. Okay, so it's going to be that term there. It's going to be K times that whole term there. And then we can just gather and simplify to obtain. Okay, so we can just again gather the terms. We can group the constant K with the first component of vector U, with the second component, and in general with the last component. Okay, and again it's easy to see that we can just replace that with the product of the scalar multiple of U with V. Okay, so that is the third axiom. Right, so what we're going to do is we're going to take the product of U with itself. Okay, so we're going to take the product with itself. Okay, and what is that? That is the weight U1 squared plus W2 U2 squared plus, we go up until Wn Un squared. Okay, now please note that these are all positive terms, and these weights that I've introduced initially, they are all positive, non-zero real numbers. So this this is definitely at least zero. The view with itself is zero. The only way that happens is if this whole term that we worked out, if that term is zero, okay? And the only way that can help, the only way that a sum of positive real numbers is zero, and remember these weights are still positive real numbers, and they're fixed, the W's are fixed. So the only way that whole thing can be zero is if ui is zero for all I between 1 and n. Okay, so again, this verifies the final axiom that we talked about. So this is definitely an inner product. So going back, we don't have to verify that question because we've done it in general. We've considered a general argument. Then this one is just to see if one understands how this particular process works. There they give the vector u and v, and they just quickly ask us to compute those two inner products. Okay, so taking those two vectors, so what is the inner product of u with v going to look like? And remember, the weights that we were given were W1, W2, and W3 respectively. where W1 is 2, W2 is 1, and W3 is 3 respectively, right? So basically, introducing those weights, we get that the inner product of U with V is pretty much going to be, it's going to be 2, that's my weight there. Okay, and then you're going to take the product of 1 with 4. Okay, and then you're going to introduce the weight 2. So that's going to be 1 times the second component. Okay, and then you're going to introduce the third one. Okay, so that's going to be third weight, and that's going to be times 1 times 0. Okay, so that's pretty straightforward. So that inner product is going to be 6. And then to just compute the inner product of U with itself, reduce the weights. Again, introduce the weights there, and okay, there we've got the weights, and then you're going to take the dot product with itself. Okay, so that's going to be plus, that's going to be again minus 2 squared, that's going to be 1 squared. Okay, so that becomes then obviously that, and so we can easily go and calculate that. Okay, so that is okay. So in the next example here they ask us actually verify that the following product defined specifically as that operation there, show that this operation is not an inner product on R2. So we need to show that one of the axioms is in actual fact violated. And I mean, let's look at the following examples. So let's take the vector U with x component 2 and y component 1. Now, if we look at the vector U, if you look at the vector U in a product with U, that is going to be, by definition, that's going to be, you're going to take the first component of U, which is 2, and you're going to multiply it with the first component of U, which is 2, okay, and then you're going to add that to the second component of U, which is 1, multiplied by the second component of U, which is 1, and that is going to be minus 3. Now minus 3 is strictly less than 0, and therefore that implies that this particular product is strictly strictly less than 0, which implies that the final axiom, which is axiom 4, does not hold. And axiom 4 specifically states that the inner product of a vector with itself must always be at least 0. So axiom 4 does not hold. So let's just go back. If we look at the axioms, you'll see that that requirement needs to hold, and that's the inner product of a vector with itself must always be at least 0. Okay, so in that case, the final axiom fails. Okay, so so that's going to imply that the product is not an inner, or rather let's call it the operation. It's not an inner product. Right. Okay. So if you need to go and prove that one of the axioms fails. Obviously, if you want to show that a given operation is not an inner product. We have some additional examples. We will look at. We'll quickly look at the proof of the first example and the third example. First example is, again, you've got the vector space of 2 by 2 matrices where the entries are real numbers, and you're asked to show that this particular product defined in that way, it defines an inner product on the vector space M22. So how's this operation defined? It's pretty much you take the transpose of U, you multiply it with V, and the resulting matrix, you calculate the trace of that matrix. And we just want to briefly show that defines an inner product. So we just need to quickly show that the axioms are satisfied. Okay, so if you take the inner product of U with V, then that, according to the definition, that's the trace of U transpose times V. Now remember that the trace of a matrix is the same as the trace of that matrix's transpose. Okay, so that is going to be the trace of the matrix V's transpose with U's transpose is transpose. Okay, and we know that that is the trace of V's transpose times U. And that is the inner product of V with U. Okay, so my first axiom holds. If we take, we introduce another 2 by 2 matrix W, then we know that that inner product is going to be the trace of the transpose of the matrix U plus W multiplied by V. Okay, and that is going to be the trace of U's transpose plus W's transpose, because remember the transpose distributes over the sum between two matrices. Okay, and we're multiplying that with the matrix V, and that's going to be the same as the trace of U's transpose V plus W's transpose V. Okay, and the trace always distributes over the sum. So that's going to be the trace of U's transpose V plus the trace of W's transpose V. Okay, and that's the inner product of U with V plus the inner product, well, we cannot call it an inner product yet, so my apologies for that. We first have to show it. So there we get that's the sum of the product of U with V and W with V. Okay, so the second axiom holds. Then the third axiom, we just need to check that the scalar multiplication property holds. This is very straightforward, so that's just going to be K multiplied by the trace of U's transpose V. Now, again, by the properties of traces, we have that that is going to be the trace of K times UTV. And again, by the properties of transposes, we have that that is going to be you can replace KU transpose with that transpose. Okay, and that is just going to be the inner product, well, the product, not the inner product yet, of KU with V. Okay, so the third axiom holds, and the last axiom we need to show that U's product with itself is bigger than or equal to 0. That's the one part we need to show. That's going to be the trace of U's transpose with U, and we just need to make sure that that in fact is bigger than or equal to 0. So there we've got the transpose, and so let's just multiply this matrix out and see what we get. So we take the U's transpose with U, and again that is not difficult to do, so working that out we get that that's equal to, we're interested in only the entries on the diagonal because that is what the trace is going to be. So we are not interested in that, and then we calculate the entry in the second row and the second column, and that's going to be U12 squared plus U22 squared. Okay, so then working the trace of this matrix out, the trace of this matrix is the sum of the diagonal entries, and that is very straightforward. Okay, so there we've got the trace, and that we know that is equal to the product of U with itself, and that's a sum of positive real numbers, and so that's always going to be 0. Now also note that that this product here, again, if you look at the product of U with itself, that is 0 if and only if this trace that we worked out here is 0. And basically the only way that can happen, again, the only way that the sum of positive real numbers is equal to 0 is if each one of those real numbers is equal to 0. So that means U11, U22, U12, and U22, they must all be equal to 0, which can only happen if U is in fact the 0 vector. Alright, so we've proved that the fourth axiom holds. Fourth axiom, always first show that your defined product, if you take a vector as product with itself, it's always bigger than or equal to 0, and the only way that your inner product of a vector with itself is 0, exactly 0, the only way that can happen is if the vector itself is the 0 vector. Okay, next up we've got the evaluation inner product of Pn. Now remember Pn, how did we define Pn? It's all polynomials of degree at most n. So how this product is defined, remember the vector space Pn as well, is you take, if we look at P2 specifically as an example, how this product works is you take two polynomials, P and Q, and then you introduce real numbers x0, x1, and x2. And then what you do, how you calculate the product, is you basically work out each function P and Q in the points x0, x1, and x2 respectively. You take the products at each one of those points. So that is the product of P and Q in the point x0, the product of P and Q in the point x1, and the product of P and Q in the point x2. And then you add that all together, and that is called your evaluation inner product. So let's just quickly verify that this is in fact an inner product. Right, so there we've got our inner product. Now, this isn't terribly, the first axiom is not there, it actually follows very quickly because you can just switch the P's and the Q's around. These are all real numbers, and therefore you can switch the two around there. Again, you can switch the two around there. Okay, and then again. Okay, and the last one, yeah, pretty much. Okay, and now obviously you can replace that with a QP. Right, so the first axiom holds. Okay, now introducing a third polynomial in R and P2, call it R. We have to go and evaluate that and see what happens. And by definition, that is going to be the function P plus R in the point x0. Qx0. Then the second point is going to be the function in the function P plus R in the point x0 multiplied by the function in the point x Q multiplied by the function Q in the point right, next up it's going to be the function P plus R in the point x1 multiplied by the function Q in the point x1, and then your last term is going to be the function P plus R in the point x2 multiplied by the function Q in the point x2. Alright, so we can replace this, that is the function P plus R in the point x0. That is just the same as the function in the point x0 plus function R in the point x0. Okay, and then this term here we can replace with the function P in the point x1 plus the function R in the point x1. And then lastly we can replace this with the function P in the point x2 and the function plus the function R in the point x2. Right, and then we can simplify and obtain. Okay, so grouping these terms together, we obtain that first part, and then grouping these terms together, we obtain. Right, so we get that second part there. Now we can just go and replace each one of those long terms with the required operation product to get. And so it's clear that the second axiom holds. Right, so proving the third axiom, go back to the actual operation. And then what we're going to do is if we multiply scalar multiple on both sides, it becomes that there, and then again grouping these terms together like so, it is then very easy to see that in fact is the same as taking the product of K P with Q. Okay, so axiom 3 holds. Proving the last axiom, we take the product of a vector p with itself, and we know that is going to be p in the point x0 by definition, multiplied by p in the point x0 plus p in the point x1 multiplied by p in the point x1 plus, lastly, p in the point x2 multiplied by p in the point x2. Now that is going to be p in the point x0 squared plus p in the point x1 squared. And again, we seem to be having a sum of positive real numbers, and that is most definitely at least equal to 0. Now, for this thing here, for the product of p with itself, this is 0 if and only if this thing that we worked out here, right, which is that term there, that is 0 if and only if that is 0. And that is 0 if and only if p in the point x0 is equal to p in the point x1 is equal to p in the point x2 is equal to 0. So again, that has to imply that p in the point x0 must be 0. P in the point x1 must be 0, and p in the point x2 must be 0. So what does this mean? It means that x0 is a root of p, x1 is a root of p, and x2 is a root of p. Now, recall what p was. P was the polynomial. Okay, and now again, p is a polynomial of degree 2. Now, the problem is that if px is not the 0 polynomial, then px has at most 2 roots, but remember that according to what we just said, according to the fact that remember, what did we previously state? We stated that according to the fact that we had this scenario here where those 3 points yield 0 values. According to the fact that, and remember x0, x1, and x2, these are all distinct points. According to the fact that we have that is equal to 0, we have that p has 3 roots, which is a contradiction. It's a contradiction. Okay, so whence p has to be 0. And this implies pretty much that this term needs to be 0, that term needs to be 0, and that term needs to be 0. Okay, so p is the 0 polynomial. because if it isn't, it will have 3 roots, but it can have at most 2 roots. So therefore, okay, so if P is the 0 polynomial, then obviously this is, which is pretty much equal to that, is going to be the 0, is going to be equal to 0, and vice versa. If this is 0, then it's going to force these 3 things to be 0, which is going to force P to be the 0 vector. Okay, so the last axiom holds, so therefore that is definitely an inner product.